Good evening to all. So today we will be discussing an introductory webinar on micromechanics of composite materials. So in today's webinar, we will be discussing on some of the basics of composite materials. What are the modeling schemes that are used in composite materials? What are the different scales of analysis that are used in composite materials? And what are the different micromechanical models that are used in analyzing a composite material, and what are the current trends available in the industry that are with respect to the composite materials and various job opportunities in this field. So let's begin with preliminaries on composite materials. So what are composite materials? So to begin with this, when we have a combination of two or more materials in a macroscopic scale, which forms a third material, is called a composite material. So you might have seen that have come across various materials such as metals, alloys such as steel, aluminium, etc. So these are the primary materials, whereas in metals we have something called as alloying. So where two or three metals are combined to have a homogeneous material called an alloy. Whereas in composite materials we have combination of two or three materials which are formed to have a homogeneous property, but in a anisotropic, having an anisotropic material property in a macroscopic scale. Such kind of materials we term it as composite materials. So what are the advantage of such materials is we have a very good strength coming from the mixture of these various materials in terms of strength. When we speak of strength, it's basically termed with respect to the weight of the material, and we term it as specific strength. So all the properties, when it is calculated with respect to its weight, we call it as specific properties. And the properties of composite materials, when it comes to the specific strength, it is very high compared to other materials. Similarly, the stiffness of these materials, the corrosion resistance of these materials, fatigue life, wear resistance, temperature dependent behavior, and other thermal properties such as thermal conductivity, thermal insulation, as well as acoustic insulation, can be tailored for the design requirement. That is the most important thing of these composite materials. These materials can be tailored with respect to the design of any component or system. So what are the different types of composite materials that are available? So there are mainly three types of divisions in composite materials. There are polymer matrix composites, metal matrix composites, and ceramic matrix composites. So in polymer matrix composites, we have a polymer which forms the base of the base matrix of the composite, and we have a reinforcement in terms of fibers or particulates that forms the polymer matrix composites. Here, um, when we say of composite materials in various applications, most of the composite materials in use today are polymer matrix composites. Nevertheless, there are various other composites which are made of metal matrix also. So they are classified in metal matrix, and we have ceramic also as a base matrix. So that forms the ceramic matrix material. So in metal and ceramics, the application of these materials defines the form of these composite materials. So basically in composite materials, what we have is a fiber material and a matrix material. So based on the type of fiber, we classify what kind of composites, and what based on the matrix, what are the different type of composites are available. So for example, when we have different fibers that are used in various composite materials are glass based fibers. We have e-glass fibers. So these are called electronic grade fibers. Many of you might have seen various electronic components which are having a board. These boards are made up of glass fibers, chalk glass fibers. So they form the fiber of the material, and the bonding material for them will form the matrix. So they are in a polymer based material. So glass fibers, one of the simpler example is the electronic board. And when we have different type of glass, glass comes in different grades based on the strength of this glass fibers. We have E glass fiber that is used for electronics, S glass fiber which are having high strength properties. They are used in various automotive and aerospace applications, and these are in forms of continuous fibers. Similarly, we have Kevlar and carbon fibers. In carbon, again, we have different forms of fibers based on their strength. They are having different terminologies. Again, they are in form of continuous fibers or short fibers. So they form basic fiber layers. So once we have these fiber layers, various materials, not only glass, carbon, and Kevlar. So we have various other fibers in terms of they are boron fibers we can are available, and some of the other fibers are based on biodegradable, such as jute fibers. Um, and various other naturally available fibers are also available. So they form the basic fiber layers, and then a bonding layer of epoxy. In terms of in case of polymer matrix, we will have epoxy as a matrix material. So they are used to form the composite material at a very basic level. We call it as lamina. So each lamina will be now formed in different segments. So they are stacked layer by layer to form a laminate. So based on the design requirement, number of layers will be defining the thickness of the composite. These are the basic things that are used in forming a polymer matrix composite. So, but whereas in metal and ceramic matrix composites, we can find short fibers or particulates as a reinforcement material for the base matrix composite. So in these terms, again we can categorize the composite into fibrous composites or particulate composites. If the reinforcement material is used as a particulate, then we term it as particulate composite. Or if we have fibers in terms of continuous fibers or short fibers, we call it as fibrous composites. Again, when we speak of fibrous composites, these fibers are unidirectional, and they are not restricted to be in one direction. We can also have fibers in two directions. We call it as bidirectional fibers, and then the weaving patterns will be different. So we have satin fibers, which all forms various type of directional properties. So from this very basic of fiber orientation, the strength of the fibers and with respect to their loading directions change the properties of the overall composites, which makes it as uh, directional dependent. So based on the design configuration, we can align the fibers in the required direction, and the composite will be having tailor-made strength in those directions according to the design requirement. So that's the basic of composite material, how the composite materials are getting strength based on the design requirements. These are tailored to form in the direction of requirement. So with this thing, so why we need composite materials, as I was saying that most of the advanced composites are made up of polymer matrix composites such as epoxy, polyester, urethane, and I forgot to mention these reinforcements are generally very thin in their diameter. So these fibers are usually in the range of micrometers. So each fiber will be in maybe not more than 10 microns in diameter. Each such fibers form into a towel, and these towels are further formed into a fabric layer. These layers are then taken to form a layer of one composite lamina. So, for example, simple graphite carbon-based epoxy is approximately 5 times stronger than the steel by specific strength. If we speak of specific strength for a particular component which is made up of steel, and if we compare the similar component which is made up of carbon or graphite based composite, we can see that the weight of the composite is almost 5 times less, and as well as it will be stronger in terms of its specific weight. So one of the main reason for using composite material is their low cost of production with high specific strength, and comparatively easy and simple manufacturing principles. So in most of the time, we have these composite layers we obtain in terms of tapes. These tapes are cut according to the orientations that are specified from the design requirements, and each layer is stacked on top of other, and then these are subjected to an autoclave curing. So thus forming a simple process of making a composite material for a simple application. So coming to the applications, many of you might have aware that most of the aircraft components are made up of composite materials. For example, very new aircraft such as Boeing 787 and Airbus 350. These are some of the newest variants of aircrafts which are having most of their primary structural members made up of various polymer based composite materials. The wings, for example, of 787 and some part of its fuselage are also made up of carbon based composites. And in terms of these are some of the new variants of aircrafts, but when it comes to the application and its usage in the historical view, so from long time composites has been used in aircraft industry mainly because of its high specific strength. So it has a very low mass whereas very high strength, so it makes a very suitable material for its application in aircrafts. And next is some of the engine components, specifically as the requirement is to have a very low weight but with high strength, especially the fan blades and the nacelle components are made up of composite material. And we can see that there are requirement of very high strength materials subjected to high rotational speeds in terms of engine components, because these components will be operating at very different temperature as well as loading conditions. So for these loading and temperature conditions, composites are tailor-made for this application. So that gives a lot of advantage in terms of load carrying capacity as well as lowering the cost and weight of the overall aircraft. So some of the more applications are in space applications, where most of the satellite parts are made up of composite materials. Again, the main idea is to save weight. So, and one more, most of you are aware of these space shuttles. These are having very specific missions where the temperature of the re-entry shuttle increases to a very high amount of temperature. So some of these parts of these aircrafts are again made up of ceramic matrix composites as well as carbon composites. So various applications again are not limited to aerospace programs, but also in various sectors such as renewable energies. We can also see these applications which are used in windmills, and again in various transport sectors such as in marine applications such as in ships. We are now seeing various applications of composite materials. So these are not only these are some of the applications, but these are not limited to these applications. We can also see in various automotive sectors also. So just a small comparison of various markets. What is the value and volume of various market sectors? These numbers are growing day by day. So in aerospace, as I spoke, so value of up to 21% and more is occupied by composite materials, and by volume more than 4% we can see. So few of the fighter aircrafts even go for up to 95% of composite materials. So building and construction, we have a very good up to 18% value, and volume of 27% of building and construction materials are made up of composite materials. And in consumer goods, we have 10% by volume and 9% by value. So coming to electronics and electrical components, again, we can see that we have a good amount of 10% by value and 16% by volume of these parts are made up of composite materials. Similarly, in marine, pipe and tank, transportation and wind energies, you can see that good amount of composite materials are used by value and by volume. So these values are keep on increasing as and when the applications of composite materials are increasing. So various industries are opting for using lightweight composite materials as compared to the traditional metals. So coming to the specific properties of the components of composite materials, for example, the carbon fiber has a Young's modulus of more than 250 GPa in longitudinal direction, whereas in transverse direction it is more than 30 GPa. Whereas the glass fibers are having around 60 to 70 GPa, that is high strength glass fibers, whereas epoxy matrix has a strength modulus of around 3 to 4 GPa. But when we combine these carbon fibers and glass fibers into epoxy matrix, the overall combination of these composite materials varies, and then we can find a very good composite material which will have a substantially good modulus as compared to its base epoxy matrix. Similarly, when we see PMCs, again one example is silicon carbide fibers are used there, and titanium matrix is used. So again we can see that the core component of the fiber has around 400 GPa of Young's modulus, whereas titanium matrix is having more than 100 GPa. So when we form the composite material, the modulus of the composite material will depend on the fiber and the matrix properties. So serviceability of this composite material is a vital parameter when we consider the application of these composite materials. So the service of the main service temperature of the main particle depends on the matrix of the composite materials. The Young's modulus and specific strength of the various composite materials with respect to its maximum service temperature is shown here. So epoxy based composites are having service operation temperature around 450 Fahrenheit, whereas ceramic based composites are having a service temperature of more than 1200 Fahrenheit. So we can see that when we have a high strength carbon epoxies, which is having a 90-degree transverse layer, we can see that the strength as well as the modulus is on lower end, whereas the same composite, when it is oriented in 0-degree layer condition, will possess a good strength and stiffness. So based on the service temperature of the component, various metric systems are chosen. Again, we can also observe that if we vary the volume fraction, that is the amount of fiber and matrix that is used in the composite is varied, the material properties again varies with respect to the volume fraction. So this also gives a small range of properties that can be tailored in. So with this basic understanding of composites, we will now discuss a little bit on what are the advantage of modeling composite materials. So one can always say that any design or any structural design requires a lot of iterations, and when it comes to composite materials, if you are directly going with a prototype and doing your design activities, then it will involve a lot of experimental and a lot of economical cost effectiveness will not be there if you directly jump into making a prototype. So modeling of composite materials or in terms of modeling any structural component before making a prototype gives a various advantage over designing, reducing the design cycles. It will also help in improving the reliability of fabrication process. So in fabrication process, there could be a lot of uncertainties when it comes to predicting or capturing the correct requirement of the component. So when you do modeling activity, so those uncertainties are removed at initial stages, whereas at the final stages, good quality control will give you control over the fabrication process. But at initial design cycle, modeling will help you in improving the reliability. Again, with this modeling techniques, you can simulate how the material and structural response of the intended material you will be able to handle from this simulating the responses. So the major challenges in modeling these composite materials is what will be the damage accumulation in the composite materials that will be happening when you subject to various loading conditions. So this is very vital because the damage mechanism that is involved in composite materials is very different than traditional metals and alloys. So that is mainly because the ingredients that are used in developing a composite materials comes from the various very basic of micromechanical approach, because we have a very uh, small structure in that the fibers which are having a micro scale, whereas the overall structure of the composite will be in a macro scale, but the damage accumulation will start in the micro scale. So damage accumulation in terms of micromechanics is very important when it comes to analyzing your whole structure. So modeling of this is one of the challenges that has to be handled. So Further, the damage accumulation will lead to failure. So prediction of failure in a complicated structural level is again a challenging task. So this requires a fundamental understanding of micromechanics that is involved in damage accumulation, as well as the strength and stiffness predictions that are used in analyzing the composites. So further, failure that is mainly due to the strain dependent loading. Strain dependent loading is basically the time rate at which the load is applied. If it is varying, then the failure mechanisms will also change. So that is a very basic understanding of strain dependent loading, and the effect of that in modeling the composite material is also a challenge that has to be addressed.